2, 1.
Don't worry, we'll get back to that. So, since my last video, I've been working like a madman to get my project finished, and I'm happy to say that everything's done. All the parts are ready, and all that I need to do now is assemble it and test it. So to kick things off, I figured I'd show you the fully assembled TVC mount that I've been working on since the last video. And in case you're not familiar with all this, the TVC mount is what's actually going to be controlling the rocket motor. I should also mention all the code and 3D models that you see in this video are available on my Onshape and GitHub. So if you want to go see those, I'm going to put the link in the video right now, and also I'm going to try to put it in the description. So back to what I was doing. A few seconds ago I just powered on the flight computer, and it takes a few seconds to boot because it has to go through a few different procedures. But after that, the TVC mount is going to quickly calibrate itself, and then it's going to actually be able to move in reaction to how the flight computer is oriented. So as you can tell, it's pretty jittery right now, and that's because at this point I was still tuning the control system. And so I'm not entirely sure how this is going to affect the flight and testing, but we're going to find out. And that brings me to one of the biggest parts of this entire project, which is actually tuning the control system, which is pretty difficult. But you'll see later on how I did that by building my own simulation. So let's get to the first real test, where I'm going to be testing the pyro channels. Okay, great. So we validated that our pyro channels work, meaning that we will be able to deploy our parachutes. And during this test, I also collected voltage versus time data. And this was really surprising to me because I thought that there'd be a dip in the voltage right as the pyros were being fired. However, as you can see, this isn't the case. Additionally, this is important because it validates my circuit design. Now, the next step is to tune the control system. And to do that, first we need to find something called the moment of inertia. Moment of inertia is a measure of an object's resistance to rotation. It is a property of an object and is defined by the mass of the object and the distribution of that mass. This measurement is important to us because it'll help us determine basically how fast the rocket will rotate based off of a given angle for the thrust vector control mount. I could calculate this value, however it will be easier and more accurate to just directly measure it. I accomplished this by swinging the rocket like a pendulum and measuring how long the period of the oscillation was. I then took this information and a few other measurements to determine that the moment of inertia came out to be 0.043 kilograms per meter squared. And this brings me to one of the parts I'm most excited about, which is the simulation that I built to help me tune the control system. For right now it's pretty rough and it doesn't have a true user interface, so it just runs on a terminal window. However, I think it's pretty useful. As you can see, the purpose of this program is to help you find the 3 gains for your PID controller. If you don't know what PID controller is, I'd suggest you look it up. But in summary, it's basically the control algorithm. It took a while to figure out what was the best way to find optimal PID controller gains, and I used a few different advanced techniques, including gradient descent, genetic algorithms, grid search algorithms. However, what I found actually worked the best was to literally just by doing a bunch of random values of the simulation, see whatever worked best, and scoring it based off of what is called the root mean square error. Then search for what random PID controller gains gives us the lowest error score, and then those are our final gains. There's definitely a lot of room for improvement with this simulation, especially with the user interface, which I plan to do in the future. And I'm not even sure if this simulation works, which is part of the reason why we're testing it in this video, which I think is pretty exciting. So if you've been following along, you have to put in a bunch of parameters, and then the simulation runs thousands of iterations. So this takes a little bit of time, so I actually sped up the video a little bit. What the simulation is actually doing is that it assumes the rocket is at some initial starting angle set by the user. So let's say minus 10 degrees in this case. It then simulates how the PID controller and rocket react to account for this error. Then, at some point in time specified by the user, a second force, such as a gust of wind, is then applied to the rocket system. A graph then shows up that shows us the position of the TVC mount and the rocket over time. As you can understand from the graph, the rocket started initially at -10 degrees, and then quickly corrected and overshot a little bit. Then, later on, at about 1/4 seconds, a second force was introduced, and the rocket quickly responded and corrected that. The optimum PID controller gains are then printed back in the terminal window. And if anyone's curious to see what would happen if, let's say, we set the 3 PID gains to 1, 1, and 1, then the following graph will show you. As you can see, it's not very effective, and our rocket would definitely crash. Now, before I strap the rocket down and test fire it, I just want to quickly show you guys what's going on in Onshape. So as you can see, this is the rocket fully built in Onshape. Well, minus a few small details. Here I'm just doing a quick section view so you guys can see what's on the inside. The internals are fairly simple, and that was by design. First I was shown the nose cone, and then where the flight computer is. In between them is where the parachute and recovery equipment is. Then I was shown the thrust vector control mount, which for some reason decided to act all funky, but you get the general idea. And with that, I'd say we're ready to do the static fire.
5, 4, 3, 2, 1. Oh, that's very bad. Blew up.
This was a disaster. If you couldn't tell what just happened, the rocket motor blew up and destroyed all the electronics, which is very unfortunate. At the end of the day, I would chalk this up to the rocket motor I used, which was an ST's E12, which is notorious for blowing up. In fact, this isn't even the first time that this type of rocket motor has blown up on me. So all this means is that, unfortunately, I'm gonna have to start from scratch again. However, this wasn't a total failure, and I learned a lot from it. It showed me how I can improve my software, my hardware, and my mechanical design. Also, if you look very closely, right before the motor blows up, you can actually see the TVC mount slightly correct the motor's position. Finally, I also got some data from the SD card. So if you enjoyed today's video, please like and subscribe and stay tuned because I'm not done yet. Thank you, and I'll see you next time.